Okay, let's unpack this. We are diving into a topic that really defines the speed of the modern world: high-performance computing.
Right.
Whether you're talking about training these massive AI models or, running complex simulations, the demand is always the same.
Maximum density and maximum speed.
Exactly. And that's creating a serious heat problem.
A huge one. I mean, that pursuit of density has pushed our physical infrastructure to its absolute limit. We're talking about data centers where the old way of doing things, just, blowing cold air around, it just can't keep up anymore.
The heat output is just too high.
It's astronomical.
So our mission today is to really give you a shortcut to understanding this essential shift. We need to get into why air cooling is failing, and then we're going to do a deep dive into the 3 main liquid cooling techniques.
Right. We've got direct-to-chip, immersion, and rear door heat exchangers, and we need to explore the trade-offs of each one.
The core issue really is just how much computing power we're cramming into a single rack.
The densities have just exploded.
Yeah.
Your sources are pretty clear that traditional IT cooling, it just hits a wall.
At what point?
When rack densities go past, say, 30 kilowatts, maybe 40 at the absolute top end.
And for modern AI deployments with the latest GPUs, that's not the finish line, that's the starting point.
That is the starting line. Those powerful chips generate so much heat in such a small space that air it can't pull that energy away fast enough.
It's like trying to cool a blast furnace with a desk fan. It's just not going to work.
Right, it creates thermal stress, but the moment you bring liquid into the equation, you change the whole game. The first big benefit is just raw energy efficiency.
Okay.
Liquid can carry heat away something like 3,000 times more efficiently than air.
3,000 times. Okay, that number alone should get your attention. And that leads directly to the metric everyone in this industry obsesses over, which is PUE.
That's right. PUE, or power usage effectiveness. It's basically the gas mileage of your data center.
So it's the total power going in versus the power actually used for computing, right?
Exactly. A PUE of 2.0 means for every watt you use for compute, you're using another watt just for cooling and overhead. You want that number as close to 1.0 as you can possibly get.
And liquid cooling helps you get there.
Oh, it pushes PUEs dramatically lower. You need less energy for fans, for chillers, for all the HVAC stuff.
Okay, so we get better performance because we can run hotter, denser racks, and it's more efficient.
It's a very compelling argument.
So let's start with the method that's really leading the market right now. Direct-to-chip cooling. DTC. You could call this the precision strike of the cooling world.
Yeah, DTC is the most widely adopted method, and that's because it integrates pretty easily into data centers that are already built for air cooling. The philosophy is surgical.
Don't cool the whole room.
Right. Don't even cool whole server. Just cool the handful of components that are generating, 80% of the heat.
And the key to that is something called a cold plate. So break that down for us. What is a cold plate?
It's actually very elegant. A cold plate is just a piece of metal, usually copper or aluminum, with these tiny little channels inside for liquid to flow through.
And this sits right on top of the processor.
Directly on the CPU or the GPU. It completely replaces the big clunky heat sink you'd normally see. The liquid flows through, absorbs the heat right at the source, and carries it away.
So if you opened up a server, you'd see these small flat plates with little pipes coming off them. The sources call them the blue and red lines.
That's it. The cold liquid goes in the blue line, the hot liquid comes out the red line, and that hot liquid has to go somewhere.
Which is where the CDU comes in.
Exactly. The coolant distribution unit. It's the brain of the operation. It sits in or next to the rack and manages the whole thermal loop.
And the CDU, that's more than just a pump, right? It's controlling everything.
Oh, absolutely. It's managing pressure, the flow rate, the temperature, but critically, it manages 2 completely separate plumbing loops.
Okay, this is a really important distinction.
It's fundamental for reliability. The first loop is the internal one. It runs between the CDU and the cold plates on those very sensitive, very expensive chips.
And that's using a specialized fluid.
High quality, super clean fluid. Then the second loop connects the CDU out to the building's main cooling system, the cooling towers, the chillers.
The facility water.
Right. And the beauty of that is that the, let's say, less clean facility water never, ever touches your high-value IT equipment. The CDU is just a heat exchanger between the two.
So clean liquid cools the chips, gets hot, dumps its heat to the facility water inside the CDU, and then goes right back to the chips.
It's a perfect compartmentalized system. It ensures a problem with the building's plumbing doesn't take down your multi-million-dollar AI cluster.
Okay, but let's introduce some friction here. This sounds great, but what about maintenance? You're dealing with liquid inside a live server rack. That has to be tricky.
That is the big trade-off for DTC. The initial cost is manageable, but the operational side, the OpEx, can be higher. You've got all these little couplings, and if a seal fails, well, you have a problem.
A wet problem.
A very wet problem. But the benefit outweighs that risk when you look at protecting the chips. These high-end GPUs, they simply can't run at their full potential without DTC. It prevents the kind of thermal stress that kills them prematurely.
So DTC is the surgical approach for the chip level. But let's shift gears completely. What if you just threw the whole server in a bath?
Right.
It sounds crazy, but that's basically immersion cooling. Here's where it gets really interesting.
Immersion is the radical approach for sure. Instead of pumping liquid to specific parts, you submerge the entire server motherboard, drives everything inside a sealed tank full of a special fluid.
And that fluid is obviously not water.
Oh, definitely not. It has to be a non-conductive dielectric fluid.
Yeah.
It won't conduct electricity at all.
What's it made of?
It can be anything from a kind of mineral oil to highly engineered synthetic fluids that are way more expensive but much better at transferring heat. The heat just gets absorbed by the liquid all around the components.
And wait, if the whole thing is submerged, that means no more server fans?
0 fans. That's a massive difference. No fan noise, no power being used by fans, and no dust getting sucked into the machine.
The density you could achieve must be incredible.
It's unparalleled. You can pack things in so much tighter. But let's go back to that friction point. Operational challenges.
Yeah, if a server fails, I can't just slide it out of the rack. How do you service something that's swimming in oil?
That's the biggest hurdle, the logistics. You need special lifts to get the server out of the tank. Then you have to let all this fluid drip off before you can even touch it. It can be messy.
And expensive, I imagine. The fluid itself can't be cheap.
It's a huge upfront cost, tens of thousands of dollars just to fill one tank, depending on the fluid. So you're making a big bet.
A big CapEx bet, hoping for huge OpEx savings from the power efficiency.
Exactly. And the heat removal is incredibly efficient. The warm liquid gets pumped to its own distribution unit, which then exchanges the heat with the facility cooling system. You can even use that waste heat to, say, heat the building.
Very sustainable.
Very.
Okay, so we've got DTC for precision and immersion for maximum density. Both of them are pretty significant changes. But what about all the data centers that are already built and can't just do a total refit?
Right. They still need to boost their cooling.
That brings us to our third solution, the rear door heat exchanger, RDHX.
The RDHS is the pragmatic choice. It's the immediate, effective retrofit solution for an existing air-cooled data center.
Functionally, what is it? I mean, it sounds like what it says, a door.
It literally is. It's a specialized liquid-cooled door that replaces the normal metal door on the back of a server rack. Think of it like a big flat car radiator.
And the magic happens when the hot air from the servers hits it.
Precisely. So the server fans are still working, pulling cool air from the front and blasting hot air out the back. But instead of that hot air going into the room,
it has to go through the door first.
It passes through the heat exchanger door and a cooling loop inside that door. Usually just water strips the heat out of the air instantly.
So you're trapping the heat at the source before it ever contaminates the rest of the room. And the sources say, this is critical for when the building's main AC just can't keep up.
It saves the day for older facilities. By pre-cooling the air right at the rack, you dramatically lower the overall heat load on the room's main cooling system. It lets the old infrastructure keep working effectively, even with much hotter racks.
So it makes the building's AC look a lot better than it really is.
Pretty much, yeah.
It seems like a lower cost way to get into liquid cooling. But what's the limit? Can an RDHX cool an 80 kilowatt rack?
No, that's its limitation. It's still fundamentally an air-based heat removal system. It's limited by how efficiently you can transfer heat from air to liquid. It's great for taking a 15 kilowatt rack up to 30 kilowatt, maybe 40 kilowatters. But if you need to go higher,
you need to go to DTC or immersion?
You have to. RDHX is for modernization, not total transformation.
That really clarifies the landscape. DTC for precision, immersion for density, and RDHX for a pragmatic retrofit.
I think that's a perfect summary. We've walked through the mechanics and the trade-offs. To recap, DTC is surgical, immersion is total, and RDHX is supplemental.
So what does this all mean?
What this all means is that liquid cooling isn't some optional extra anymore.
It's essential.
It's the fundamental engine that's required to power this whole AI revolution. The sources are clear. The limiting factor for data centers now isn't processing power, it's cooling capacity.
And this shift enables not just the performance we want, but the sustainability the planet needs with that better PUE.
Exactly.
So when you look at these workloads that are only going to grow, it seems pretty obvious that any new infrastructure plan that doesn't include liquid cooling is, well, it's just not future ready.
It's not. The cost of running high-density compute without it is becoming unjustifiable. And that really leaves us with a final thought for you to consider.
Okay.
Given that liquid cooling is now required for both performance and for sustainability, what does that really mean for the lifespan and, more importantly, the budget for all future high-density infrastructure? This stuff needs specialized plumbing, specialized fluids, specialized maintenance. Are we getting to a point where data centers are less like real estate and more like, I don't know, specialized high-cost chemical processing plants?
A fundamental shift in what a data center even is. That is definitely something to chew on as the future continues to heat up.